All right. Good morning, everyone. So it's a pleasure for me today to introduce Boyuan, who most of you know. Boyuan has been coming on 6 years, I think, as a student in the international school, and subsequently as a master's student in the virtual construction lab. And Boyuan's topic concerns collaborative multi-domain cloud building information modeling. When I shared with my family the name of one of the papers, they said, "Oh, it has every keyword possible." Good title. So you have all the keywords. Hopefully you'll explain each one so we all have a sense of what it's all about. And good luck for your lecture.
Thank you, Rafa, for the...
Again, as I said yesterday, remember to turn off cell phones.
Thank you for the introduction. Hello, everyone. My name is Boyuan Ouyang. Welcome to my master degree seminar lecture today. The topic of my research is Foundations of Collaborative Multi-Domain Cloud Building Information Modeling. And this research, of course, was conducted under the supervision of Professor Rafa Sachs. So let's begin with some introduction and background under the context of which my research was carried out. So the architecture, engineering, and construction industry is that we are all involved in is a highly fragmented industry. And if we narrow down to the design phase of construction projects, it means that dozens of design teams could be involved in the design of a single building, and each responsible for a specific design discipline like architecture, structure, mechanical, and so on. The diagram here on the right is to demonstrate the diversity of BIM design softwares that could be used in a single project as a result of this fragmentation nature. And we have to understand that different design softwares usually have schemas that are incompatible with each other, since they are each designed for a very specific use. And companies tend to keep their proprietary schemas confidential to protect intellectual properties. And to a great extent, this hinders communication across applications and making interoperability very difficult. So there are a few existing solutions that tries to address those obstacles. First is to create a direct interface between two softwares through APIs that maps actually one software schema to another. The second is to create common data schema for that multiple software adopt to use as their native schema. But in reality, none of these two solutions are implemented on large scale because they require very strong business agreement between companies and a huge effort to maintain. The last and probably the most widely accepted solution is to create a universal third-party open exchange schema based on which software vendors can implement their own proprietary export and import to release and consume information. This exchange schema is known as the industry foundation classes. So what is IFC, or industry foundation classes? Essentially, it is an international standard model documented in ISO 16739 for building planning, design, construction, and management. IFC is a non-proprietary platform-neutral data schema that covers multiple IFC design disciplines. A typical design workflow with IFC could be the following. The architect first create their architectural model in an architectural BIM software, let's say Revit, and they export the Revit native model as an IFC file, which can then be imported to the structural and the MEP software, let's say Tekla Structure and AutoCAD MEP in this case. The structural and the MEP engineers will then use the architectural IFC model as a reference for their structural and MEP design. And finally, all three models in IFC format will be brought together into a clash detection tool to check for inconsistencies and design errors. And in case of any inconsistency, the designer will go back to their native BIM tools to fix the models manually. The whole process will, of course, repeat for many iterations until the designs mature to an acceptable level. Some of the characteristics of such an IFC-centric design workflow are the following. First of all, the designs are sequential instead of concurrent, meaning people wait until others models are ready before they engage into design. And secondly, the design coordination happens only at the very late phase of the design, when all the designs mature to a certain level, and the coordination is done manually. And thirdly, people only use others' models as references, and so the models actually end up being standalone files without any meaningful connections between them. So what do I mean by connections between models, or why should they be connected? We understand that different design discipline and different design models are just the different views of the same physical building from different domain experts' perspective. And we as people with experience can infer of the information just by comparing these discipline models side by side. For example, the attachment relationship between the radiator and the architectural wall, as well as the correspondence between the architectural wall and the structural wall, should be quite obvious to us. But these semantics are currently entirely missing from the federated models because current technology doesn't support the generation and the expression of them. So our claim is also quite simple. We believe that these semantics are the basis for design coordination because they dictate the interdependent behavior of objects according to the designer's intention. Their current absence is, in our opinion, a key obstacle for realizing a more automated and more intelligent design collaboration paradigm. So what we observe from the current practice of design collaboration is that they remain, first of all, fragmented and sequential, in the sense that people prefer to wait until information from other disciplines are ready before they engage. Also, people package information into files and exchange information in batches. And thirdly, people coordinate their design manually to maintain the consistency between different design models, while machines are not taking any proactive actions in automating this repetitive coordination process. We believe the main reason is that current BIM system cannot understand the interdependencies between building objects across domains as a result of the lack of semantics. So with the stated problems, we have came up with this research objective of exploring a technology foundations for a platform that can be placed on the cloud for multidisciplinary BIM collaboration. The key features of this new platform is that, first of all, it should allow the explicit representation of object associations to register design intent. Also, we want to utilize those explicit relationships for developing applications that can hopefully shift the current practice of manual design coordination to a more automated design coordination paradigm. So now that we have a clear research goal, we can move on to the review of the state of the art to see what others have tried done to solve the problem. Here we choose to do a thorough investigation of both the commercial world and academia. On the commercial side, we have common data environments for centralized and regulated information exchange across professions. And on the academia side, we have knowledge graph representations of building information for standardized publication of discipline information on the web. We also have linked database common data environments for accommodating heterogeneous building information and data coming from different sources and disciplines. And finally, we have semantic enrichment of BIM as a technique to recover the implicit information and make them explicit to machines. So let's begin from the commercial side. In short, common data environments can be defined as digital information platform for centralized project data storage and access. This concept was first introduced and documented in the ISO standard 19650 with the intention of regulating the process of sharing information across AEC disciplines. Then software vendors have came up with their own cloud-based common data environment solutions. And some of the well-known ones are Trimble Connect from Trimble, and BIM Collaborate from Autodesk, etc. Despite coming from different vendors, most of these commercial CDEs actually share a lot of features in common. That includes design annotation, documentation, logging of historical versions of models, inter-user communication, and clash checks. So here I want to give an objective summary of the capabilities and the limitations of the current commercial CDEs. For the first part, like CDE can indeed alleviate some of the cumbersome design collaboration processes by first regulating the process of information exchange across AEC disciplines, as I explained before. Second, it provides a centralized repository for all kinds of building models and project documents. And thirdly, it offers auxiliary tools that help people in coordinating their designs. But on the other hand, we have found that almost all commercial CDEs now, they are merely file-based data management systems, which entails that the resolution of coordination is confined to a file level, and it cannot go any deeper. Also, they cannot automate any of the repetitive design coordination tasks. And thirdly, they do not provide the infrastructure for expressing the intended associations between objects across models that we think are essential for the next generation of design collaboration systems. So recently in academia, there's this trend towards the use of knowledge graphs within the built environment for representing building information. They use a relatively simple language and concept, namely a graph-based model consisting of nodes and edges to represent the information. Yet they provide a lot of structured content and meaning if we apply them appropriately. And for us, there are two very important features associated with knowledge graph that made us believe that this could be the appropriate way to represent building information under our multidisciplinary setup. First, it provides a unified data model for semantics, namely the RDF plus L ontologies for standardized representation of building information across every discipline. And secondly, the graph nature of the data model makes it very easy to express associations between entities because they can be represented as simple as edges that connect two nodes in the graph. So some of the milestone achievement in this area of research are the following. First of all, around decades ago, researchers have already suggested that knowledge graphs can be the basis for expressing association semantics across objects in the AEC discipline. And these explicit semantics can open up opportunities for more advanced applications. Then comes the development of IFC-a, which explore the graph nature behind IFC schema. And they actually transform the entire data model into an ontology so that every IFC model instance can be converted very easily to their knowledge graph representation later on. And in more recent years, researchers in this field have worked together and gradually formed this community of linked building data, LBD. So more recently, linked database common data environments has been a thrust area of research within this LBD community. It was proposed to address the issue that not all types of building information can be conveniently expressed in graph formats. The basic idea behind this linked database CDE is to embed core building semantics into RDF graphs, which can be linked then to the extension data hosted under the non-RDF containers. But up until now, most applications in this field have focused only on the support of exchanging information that exists already. But with the abundant data now made available inside the CDEs, we see a huge potential of it supporting the automated inference of new semantics, especially those that sits between models across domains. So speaking of inferring new semantics, third and the last topic of my literature review is regarding semantic enrichment. It is a well-established fact that unlike humans, current BIM systems are only capable of processing explicit semantics. So even though I've shown how the federated design models are implicitly related one to another in so many ways, there's no way for the machines to process it and make use of it unless they are being explicitly enriched. So semantic enrichment as a technique uses AI to infer and supplements information that were not explicit in the original BIM information models. Later, two types of general semantic enrichment tasks have been identified by researchers. First, we have this group of enrichment regarding the implicit information of individual building objects or object aggregations. And secondly, we have those that enrich the implicit associations between objects across domains. Most semantic enrichment research today fall into the first category, but apparently my research will focus more on the second type of semantic enrichment. So after carefully reviewing the state of the art, we are trying to propose a new way of representing building information and to enrich building information to complete what's missing from the current technologies. Specifically, we would like to use knowledge graphs to represent core building semantics because it brings a unified data model to all kinds of building information from all disciplines, and they elevate the level or the granularity of data coordination from a traditional file level to an object level. We also suggest the use of linked database CDEs that can be placed on the cloud to accommodate the heterogeneous building data and information from different sources. Because some of this information, like object geometries, are proven to be inappropriate for graph representation. But these information are actually essential for our subsequent step, which is, of course, to find a way to semantically enrich the federated model representations by adding meaningful relationships across disciplines. Intelligent applications that can then be built on top of these new semantics and the linked graph representations to automate design coordination processes. So to fulfill the research goals, what are yet missing from the status quo are following. First, we are missing an ontology that formally defines the set of relationships, the relationships and associations between interdomain building elements that reflect human understanding of building designs. And secondly, there needs to be a technical procedure for establishing those relationships on the instance level between models. After filling these two gaps, we can imagine a range of applications that can be deployed on top of the connected discipline models and the explicit relationships. And we will actually implement some of them as validation to my research. So a slide for my research methodology. I believe my research is a pretty typical example of a design science research, which implies the awareness of problem and devise solutions. So first, we begin with the definition of problems and justifying our research motivations through interviews, discussions, and literature review. And secondly, we identify the necessary component of our proposed CBIM system, which constitute our research objectives. And then comes the actual design and development of the products or the artifacts for realizing our proposed collaboration paradigm. We will also demonstrate and evaluate our artifacts by implementing prototypes and testing their performance. And finally, we will reveal our research results to the public through conference presentations and papers. And of course, the whole process will undergo many iterations of refinements. So after all the backgrounds and the literature review, we can now move on to the actual experiments themselves. So as mentioned before, the implementation will mainly focus on the development of two artifacts. First, the and the CBIM ontology that defines the object relationships at the conceptual level. And secondly, the semantic enrichment procedure that generates association between models on the instance level. So for those who are not very familiar with the concept of ontology, an ontology can be defined as a formal, explicit specification of a shared conceptualization. And in plain language, an ontology can be understood as a formally written representation of a certain domain of interest, which is also agreed upon a group of domain experts. So under our context of multidisciplinary design, CBIM ontology should therefore serve as a formal definition for various possible semantic relationships between building elements. And the source of this semantics should come from experts' view of the object interdependencies, and they should convey design intent. So just as a remark, the completion of this ontology is expected to be a long-term iterative process, just considering how diverse these semantics could be. But one of the contributions of my research is to provide an alpha version of this ontology. So we have came up with 3 general types of object relationships for the ontology, which are the spatial relationships, the functional, and the constraint relationships. I'll explain what each of them represent in detail. So here is an overview of the first version of our CBIM ontology. It was published together with the article towards artificially intelligent cloud-based building information modeling for collaborative multidisciplinary design. You can find it online. So I will introduce here the main ideas behind each family of object relationships in our ontology. So first we have this cluster of spatial relationships. In my opinion, topology between objects is the first thing that an experienced user will infer when they look at the models side by side. And they are the most fundamental inputs for any subsequent inference of advanced semantics. Therefore, we believe that there should be a dedicated class of spatial relationships to register this topology between objects and make them explicit in the first place. So the diagram below is to show an objectified, how an objectified spatial relationship node register the topology between 2 columns in the diagram. Within this node is a set of attributes that register topology status, such as the clear distance in XYZ dimension between the 2 elements, their relative position in XYZ, and whether the 2 objects are in physical contact with each other. So that's the spatial relationship. Next, we have the cluster of functional relationships, which we consider as a more obscure group of relationships between building objects. So the reasoning is like this. Right after the expert managed to capture the topology between 2 objects, he or she can then infer whether there's any functional relationship between the 2. By functional relationship, I'm referring to like implications of the dependencies between the building objects. An example is the correspondence between these 2 columns, like we see here in the diagram. Or another example could be the hosting relationship between an architectural wall and the structural entities that it contains. These relationships to convey the intended correlation between elements in lexical terms, and they are meant for human readability. So after the family of functional relationships, we finally move on to the most implicit group of relationships, which are the constraints between objects across disciplines. So again, taking the column example, as soon as I deduce that the 2 columns are corresponding, meaning that they are the dual representation of the same physical column in the actual building, it automatically implies that there should be a set of constraints between the 2 geometries. In the example, for this example in the case, the 2 columns are probably intended to be exactly aligned with each other and occupy the same physical space in the 3D world, where otherwise any offsets between the two columns should be regarded as a design inconsistency. So how do we capture these kind of implicit constraint interpretations? The main problem we face in this case is that these constraints are quite case specific. So we have to come up with something that can generalize to most design scenarios. And to address this issue, we have to abstract people's reasoning when they infer the implicit constraint between objects. And specifically, we have adopted a top-down approach, meaning that we start from the very generic intents that should be agreed among most experts, and then we apply them onto the specific cases to obtain specific constraint. Here we have came up with two generic design intents that hopefully no one will object. The first design intent is that structural model elements in the building superstructure should never protrude from corresponding or hosting architectural model elements. This is to avoid unintended structural exposure. And the second design intent is that all architectural slabs that make up the floor of a story should always be supported structurally throughout its horizontal extent. This is an example to see how the generic design intent rules apply to a set of discipline building models. On the left and the middle, we have the architectural and structural design of the building section. When we superimpose the two models together, it becomes clear that the model displays some of the design inconsistencies. First is the protrusion of the structural column and the beams from the architectural wall, highlighted in red. And this is a non-violation of the first design intent rule, which restricts the protrusion of structural elements. And second is the missing of structural support for the bottom. And this is highlighted in blue, which is an obvious violation of the second design intent. So to construct the CBIM ontology, we finally applied those generic design rules onto the specific design scenarios for extracting the object level constraints. And I'm not going to bore you guys by going through all the details in this table. But to make long story short, we have enumerated a number of object pairs from the test models on the left. And these object pairs have all have one thing in common. It's that they have to display some sort of functional relationship between each other. And by applying the generic design rules onto these specific design scenarios, we extract the specific design intent constraints for the object, for each object pair. And finally, we abstract these constraints systematically into ontological classes. And that's how we form the constraint relationships in the CBIM ontology. So of course, only having the ontologies is not enough because they are just conceptualization of domain knowledge. We also have what's left to be developed is actually a set of association semantic enrichment procedures to actually establish those defined relationships on the model instances. So the enrichment procedures was developed in twofold. First, we have developed a rule-based algorithm, the TIOC algorithm in short, to infer the CBIM spatial and functional relationships. The underlying mechanism includes a topology computation routine, plus a set of rules that encapsulate human understanding about placement of building elements. And this algorithm was then published together with a conference paper, and it contributes as being the first known attempt for an automated inference of object relationships across disciplines. The pseudocode of the complete algorithm is provided in the paper and will be included into the thesis as well. So you are welcome to look at it if you are interested. And the second part of the enrichment procedure covers the complete instantiation of all three types of CBIM relationships, namely the spatial, the functional, and the constraints. Development of this procedure involved extensive coding, So we have implemented a three-stage enrichment mechanism to establish those relationships in a sequential or a cascading manner to maximize efficiency. So what I mean by this is that we begin by making the spatial relationships explicit. And these topological facts are then being used as an essential feature for inferring the functional relationship between objects in the second stage of the enrichment. And similarly, these functional relationships are then used as an input for the system to determine the constraints between the objects. And I believe this is also mimicking how we as humans are inferring these implicit semantics. So this is a conference paper that I referred to earlier on. The paper was presented in the AEC-a conference last 1 year in Norway. And right after that, we have prepared a manuscript for a journal paper. Cover was missing from the conference paper. So now that I've finished introducing the artifacts, I guess it's time to see how these CBIM relationships and the semantic enrichment procedure will function in action to make the association explicit. So the first validation experiment is to see how the first half of the semantic enrichment procedure will work on a real-life federated building model. And we begin with the federated knowledge graph representation of the building, where we can find information about the respective building stories that contain the two column objects. And by reading the properties of the building story, the algorithm actually first deduces that the two stories are equivalent to each other, and therefore generates an explicit connection between the two stories. And then the algorithm will perform a search over the objects that's contained within this pair of building stories. And using the geometries that's stored in the CDE, the algorithm finds that the two columns are actually in close proximity to each other, which triggers the instantiation of this objectified spatial relationship. And knowing that the two elements are overlapping, the algorithm finally performs a Boolean check on the exact geometries of the two columns, and the result is being evaluated against the embedded rule sets. And all the conditions met, a new correspondence relationship will be instantiated between the two column nodes, and the first semantic enrichment is completed. And in a follow-up experiment, we actually implemented the full semantic enrichment pipeline and successfully registered all three types of CBIM relationships. So all the nodes you see here outside of the green and the orange dots are the new associations that we've managed to generate. And there were a total of 12 constraints being explicitly added to the model in this particular example. So let's zoom into the two roof slabs to see what constraints actually have been captured. By applying the first generic design rule that restricts the protrusion of structural elements, the procedure actually established two CBIM constraints between the architectural roof and the structural roof. And this is to constrain the geometries of the two elements on both the Z dimension and on the XY projection. And then from the second design rule that stipulates the structural support for architectural slabs, the procedure actually established another geometry constraints, which specify that the two slabs have to be almost equal in their XY projection. So besides making the object association explicit, I want to also demonstrate a prototype application that was built on top of these interlinked models and the explicit semantics. This demonstration may serve as a justification to our initial claim that explicit semantics are a basis for automated and intelligent design coordination. So I think it has been made very clear that during the design phase of projects, it's very critical to keep the consistency between discipline designs. Or in other words, any incompatible design may lead to some serious errors on the construction side that needs a lot of cost and money to fix. But the dynamically evolving nature of the building designs is making it very difficult actually to keep the model consistency consistent all the time across all design disciplines. So what we have done to address this issue is to design a dedicated evaluation module for every CBIM constraint class. And these modules are made up of a bunch of software methods that we developed in Python that, first of all, parse the discipline models and evaluate in real time whether the state of the objects are in compliance with what's specified in the constraints. So to see them function in action, we begin with the two discipline models in their original states that are consistent with each other. So as we execute the constraint evaluation module, the Python function will run in the background, read the constraints, access the geometries, and make geometry computation on the fly to evaluate whether the objects are in compliance with the constraint. And as you see here in the diagram, the function, there are 12 out of 12 constraint evaluation have returned the value of true, meaning all the constraints are being fulfilled, and the machines will understand that there is no inconsistency now between the design models. But now if we imagine a situation where the architect decides to move one of his walls in the model to make space for his room, for example. Now suddenly the models become inconsistent with each other. So as expected, as we run the evaluation module again, there are several cases of constraint evaluation being found. And this is an instant indication of design inconsistency. Not only that the system can warn the user for such kind of design violation, the machine can actually infer the nature of these inconsistencies by investigating the specific combination of constraints that's being violated. And they can provide insights to the user. So in our ongoing research, we're actually trying to prove that these constraints and their evaluations can serve for the automated consistency maintenance of discipline models. And what I'm referring to here is the proactive design, proactive change propagation of design changes from one discipline model to another. So in this case, we can actually automatically regain the consistency in the structural model. And this is done in an absolutely automated fashion. So I hope that through this series of simple use case demonstration, you are convinced that explicit semantics can actually open up opportunities for some intelligent applications, and that these applications can indeed support and, more importantly, automate some of the design collaboration processes. So I want to end my presentation with some discussion and conclusion for my research. Summarizing one slide that what I've presented in the last 40 minutes or so, we have started with the claim that association semantics are a basis for realizing automated design coordination. That's our initial hypothesis. Then we realized that current BIM system and current state of the practice of design collaboration actually fall short in the sense that they do not facilitate the expression of and the generation of associations between discipline models. And in response to that, we have proposed a possible solution for a future cloud-based BIM design collaboration platform for proactive design support. And we call this the Cloud BIM, the CBIM. The main components of the CBIM system includes the knowledge graph representation of BIM models for standardized representation of information. And the system also includes a linked database CDE to host the information from different sources and multiple disciplines. This is to accommodate the heterogeneity nature of the building information. And thirdly, we have the system, the CBIM system incorporates an ontology that formally defines the set of design intent relationships between interdomain building elements. And finally, we have this CBIM association semantic enrichment procedure to instantiate those defined relationships among building elements. So the first two bullets might have been covered early in other research, but the last two bullets are at the core of my research. So in the last part of the lecture, I've also demonstrated how this CBIM concept can be applied on a set of federated discipline models. I've also demonstrated some applications that we can implement on them. So in terms of the contribution of my research, first we presented this concept of CBIM ontology. And even though there were some informal mentions of relationship across objects in earlier papers, I believe that the CBIM ontology is the first ever publicly available formal definition of object associations across professional AEC disciplines. And secondly, we have also tested the feasibility of using algorithms to infer the implicit object associations across discipline, which we believe is the first in our field. We also implemented some pioneering prototypical applications that were only made possible by the interlinked building representations and the explicit semantics. But of course, all research comes with limitations. They kind of guide us for planning our upcoming research. First of all, the CBIM ontology only covers 3 types of object relationships, and they are far from being complete. We think that it's worthwhile to evolve the ontology through time to include more semantics and make it more widely adopted. And second of all, we have only tested and validated a rule-based algorithm for the CBIM semantic enrichment procedure. But actually, for some very implicit and ambiguous semantic relationships, it might be actually very difficult to hard code the rules into programs. And for that scenario, we see a huge value of investigating the learning-based approach. And also, we didn't have much opportunity to demonstrate much of the intelligent applications that we can build on top of the CBIM concept, besides the constraint evaluation. But fortunately, we have the opportunity to include some of these applications into the manuscript that I'm now preparing with my colleague. And that includes CBIM cloud collaboration for asynchronous design and CBIM proactive design consistency maintenance. The last and perhaps a more technical thing is that we don't want the CBIM to be a completely standalone platform that's isolated from the current BIM tools that's available on the market. And instead, we want a tight integration actually between the CBIM and the legacy softwares for smooth information flow and for better user experience. And this probably suggests the need for developing CBIM plugins for existing BIM softwares. So here are the 3 publications that I mentioned during my presentation. The first 2 have been published already, and the third one is the one that I'm co-authoring with my colleague, and we're expected to submit it very soon. Here is a bibliography. And that's it. Thank you for your attention.